Okay, I'm going to close this. Okay, here's that peek at the idea capture tool, and we already got a tool question in there. That's nice. Matt and I will try to get to that, and at the end, we'll also just try to rapid fire through all of those remaining questions and improvements. This really got better by, so many teachers improving it. So keep those coming. Here is just that picture. It's sort of take your attendance by clicking on the link that Matt put in the chat multiple times. So there it is, just a peek at it. Okay. The quick situating the unit 1. So just to be really clear, it doesn't have an official PE, right? I should not say PE, performance expectations. That is where students are supposed to be at the end of junior or senior year. And we just find students are not ready for any performance expectation in the first couple of weeks of 9th grade. So we do have a big idea, and one that I want to say is maybe the biggest idea in all of physics. So even bigger than Newton's laws, conservation of energy, is the idea we can study something in the world, technically system, collect data, explore patterns, which in physics so often are mathematical models, mathematical equations, to better understand the system and predict/influence its future behavior. Just one, climate would be a perfect one. We make climate models to better understand the climate and, of course, predict/influence its future behavior, and really hit the science practices hard. Whoa, once I clicked in, it moved me, so I lost where I was. I'm going to zoom out. Okay, and just so you can kind of see it, yes, the performance expectations are light at the beginning of the year, and then as you'll see throughout the year, each unit builds more and more performance expectations, culminating in Unit 6. Unit 7, said a couple times, that can be chopped up. If you have 2 extra days before winter break, you can do one segment of Unit 7, Space and the Universe. So 6 is really the culminating. If you do leave 7 to the end, that's a great way to end the year. It's really nice to talk about space and the universe at the end of the year. So those are just some options there for you. So that's situating Unit 1 in the course of the year. So I'm just going to hop out to the agenda and just say, okay, situating the course within the whole year. And with that, I'll toss it over to Matt to just give the first 10,000 foot view of the unit itself. And I'll kind of direct to me. I'll click on Unit 1 and let me know.
Yeah.
Since I'm sharing.
Yeah, so if you haven't been to the website in a while, it was refreshed, and you click on Unit 1 on that restricted site, and you have to be logged into the Google, your work account, Google typically. And this is kind of the 10,000 foot level of all of the good stuff in one place. So at the top, it has assessment opportunities, as well as those SEPs, and then our performance expectations. And then it has an image of the unit. And then you can, as you scroll down, Bradford, it gives task narratives along with every opportunity, assessment opportunities, extra supports, materials, resources that are all linked all in one spot. So it's kind of chunked at the task level, has a suggested amount of time, and all of those opportunities are there for you to click into individual links that are there. Another thing that I wanted to point out, Bradford, if you scroll all the way to the top, there's some overview videos there at the top as well that give kind of a full overview, big level, and then a shorter overview video. Those are really helpful in that just if you're trying to get ready to teach what's coming up, those videos are there for you to access. Yeah, and I think with that, I think we want to dive down deep into some of the big highlights of the different tasks that we're going to be doing. And Bradford, you want to talk about day 1?
Yeah. Day 1 of curriculum. So, a lot of people have community builders. with yeah, obviously just community building. So day one of curriculum, although this does fit nicely towards the tail end of community building and gets students yeah, talking with each other, highly structured, and the inquiry cube. So really just low stakes. There's the inquiry cube, and I was assuming familiarity, which isn't a good assumption actually. So you just have a cube, and here we photoshopped it onto Mars, just really kind of to be cute about it. And then they are given those cubes, and you can't tell from this initial one, but you have to predict what's on the bottom. And at the beginning, it's really hard, and you don't even know. And lots of times they just want to write question mark, which is perfect. But we want to explain we want to have them think about their confidence, which is low. In science education, we are always talking about the value of evidence-based reasoning. So we want to compare a low evidence prediction, that first wild guess, and there's not meant to be pressure. So if students bring pressure, like I got to get it right, we want to encourage them to not embrace it as a stressful thing. We just want that low prediction so we can contrast it with an data-informed prediction. In fact, I just did this today myself, and yeah, went well. But in any case, you can maybe see a little bit from this cube is opposite sides share the same color. The names always start with the first couple letters. In fact, I don't want to go too deep into it on the webinar. We'll go over every little thing in the workshop on it though. But opposite sides, the number of letters in common, like sky, S-K-Y, and Skylar that you can see on this one is they have S-K and Y together, and then they each have a little number 3 in the bottom. I know that image is so small, but yep. And then the number in the upper right is the number of letters, S-K-Y-L-A-R. That's 6 letters, and there's a number 6 up there. And students discover all of that. It's pretty, within 10 minutes, they have almost all the little ones. If there's actually some hidden ones now with bolding and stuff like that, that we don't even talk about unless the student brings up. But in any case, you would just click on the teacher cube here, and it has the answer key with every pattern. Just a great one day, really try to, it could be 1 or 2 days if you mix some community building, but really just meant to kind of have most of the good stuff of science, right? Students are collaborating. If they can't see the other side, they're not supposed to pick it up and look. They're supposed to ask their colleague. Just like in science, you might not have an atomic force microscope, so you send a sample over. So we just sort of try to mimic as much good stuff in science, and we wrap up the activity with saying, what did this capture and what didn't it capture? And then the final question, since I'm on a roll, is how did we go from a low evidence to high evidence, or low confidence to high confidence? And that's tricky to write. So a lot of students can say something verbally, and we just encourage them to say it verbally and write it in just a nice little way to start the first day of curriculum with students. And there was a poster that I guess
one thing that I'll add, and Bradford, if you could go to the there's some slides. It's on the next slide, I think, as well. That this is a day, like right off from the beginning, we are trying to build competency in our students and really encourage them to talk and share, and also call out all those great things that students are doing, asking questions of each other, explaining the reasoning, showing with body language how they're working. So all of those things are kind of in place, walking around, interacting with students, and encouraging that work. This poster is introduced, the poster that Bradford's showing, where our essential question for the whole course, finding and using patterns in nature to make predictions, either in the future, data-informed decisions in the present, and understand the past. So kind of an intro and just a good activity that models a lot of what good science is about. Bradford, if you click on the next tab over, it's one over from that.
There you go.
Yep. We also are looking at the pathway to making better predictions. We introduced this right after they compare and contrast their low evidence wild guess to their high evidence guess or their data informed prediction. So really introducing the process of making better predictions, guess based off of observation. They do inquiry to determine pattern, look at the data, they talk with each other, make sense through consensus, and then ultimately make that data informed prediction. And with that, I think I'll hand it off to Bradford. You want to lead us off with starting with horizontal line?
Yeah. I'm going to try to close some of these tabs quick. Nice. All right, horizontal line. This is a second, third day, how it falls, but really nice. So want to just highlight that this is a whole class inquiry, and this is very intentional. So whole class, how do we do that? Here's a spreadsheet. So students, this is editable. A student jumps in and they grab one of these columns, and there's actually, if you look at the slides, it's really, we try to keep, students are kind of trying to really run the show. They need you as a facilitator, but some student is holding that pendulum. You have an angle checker. There's like 5 roles and 2 angle checkers, a holder, a couple people on a calculator checking that the averages all work out. But you can just see this group did 5.5, 5.2, 5.3, 5.3, 5.5. Okay, that's all good stuff. And we see there's a range. Not every student got the exact same answer. So it's very understandable. We actually talk about that, the uncertainty in a measurement. So in any case, you can just see there's a spread of data of 0.4 seconds. And this was from the summer workshop. So this was teachers. You might get there with students. It's only the first or second day of, it's the first week of school-ish. So in any case, sometimes it's more, 0.6, 0.8, but just want to stress, we have to, even with teachers, we retook the first data point 4 or 5 times. The first time there was like a range of a second from the first to the last person. So we repeat until it's within like half a second. And then the following data points come every minute. But the first data point takes 5 minutes and 5 tries with teachers and students. And just want to show how intuitive it is. Okay, so once we get to graphing, actually, I guess that's interesting. We didn't pull that up, but once we get to graphing, we will have uncertainty boxes. So I'm going to wait till we show that in Desmos. But where do they come from? Right here. And really intuitive. I know lots of times when teachers first hear this, they're like, uncertainty bars with 9th graders. Yeah, it totally works out. They know you put the data point at the average. And yeah, if we have a spread of like a half second, now I will say if the spread is 0.6 and you start in the middle, you would go up 0.3 from it, plus 0.3 or minus 0.3. So that is a lot to say in just 30 seconds on a webinar. And we spend, 5 minutes, and that's almost all it needs, because it's a light touch, exposure, practice, mastery. They'll see this again and again and again. And one thing I guess we didn't say about the first unit, if it's new to you, it is 4 experiments after each other. Experiment after experiment after experiment after experiment. So exposure, practice, mastery. Excellent. I'll throw it back to Matt to wrap up.
Yeah, so kind of on that vein of the exposure, practice, mastery, we have our students look at the pendulum experiment, and really this is the first exposure of what high school level writing looks like. And so this is the key for our pendulum experiment. I wanted to highlight, if you scroll all the way down to the bottom.
Yeah, one thing just to jump in, to show what we mean by things repeat, here's the wild guess again. They ask a wild guess about 60 degrees, just like in the inquiry cube. Guess what's on the bottom? Here, it's guess what's 60 degrees. Then we take some data and we have a data-informed prediction. And then I'll throw it back to Matt to have students talk about the conclusion.
Yeah, so this is their first go at a conclusion for us. So we have tried to intentionally scaffold and raise the level, both through this unit, but also through the year. So in this one, this is the first exposure using a like a fill in the blank sentence there, and you can see like all of those yellow parts are where they're filling in. They're getting their first exposure at what is the claim, what do we mean by evidence, looking at that math model with some reasoning and making their prediction. And then we also encourage them to, think outside of the experiment that we did with our research extension question. But you'll see, hopefully, as we are going through this webinar, that you see that the rigor and the opportunity for students to show their learning grows and grows, and we change different modes as they are building that competency of how to write at a high school level lab report. And so this is one way that we get started, but then we have others that we will show later on as well. Bradford, did you want to do the core response for that one?
Yes. Now, I thought we were going to wait till we had like 3, no, just each time. Okay. Yep. So there's a core response. If you look, and this is not for everyone, but I'll just say, I used to think it wasn't for me, and now it is one of the highlights for me. So a choral response, we try to get all students to say it, and started this a few years ago, and now we have arm movements, but we're still in early iteration. So really glad to hear it. This one is very easy and straightforward. And we always start with some things in this world. So maybe, I'll just say this one. Maybe we'll see on the webinar if anyone wants to join. But this one is just some things in this world. When you double the input, the output stays the same. And with our hands, we trace a horizontal line. And of course, you're swinging a pendulum. It's so fun. It's just really neat to do the pendulum, especially if you have like a 2-second pendulum or a 1-second pendulum, just anything like, a meter long-ish. And it's really neat how it doesn't change much at the angle. Technically, it does change a little bit, but within our accounting method, the simplest model really is a horizontal line. So there we go. That is, that's here. And we'll try it later on. There's a lot of students that respond to this, and especially students that might not just love science for science sake. The core response really is one that brings them in. So with that, let's move on, and I'll say it because we're right here. Proportional, we have a poster for every pattern, and we haven't said this even. There's just 4 patterns that cover most of 9th grade physics, IB physics, and even college first year physics. And 2 of those are, one is horizontal line, think conservation of energy, conservation of momentum. And the next one, just so common, is proportional. And proportional, and we represent it as a data table. This is the culminating thing. So I'm leading with the ending. Then there's a graphical representation. There's a mathematical equation, which we'll call, in the context of an actual experiment, we would call a mathematical model. And that's new language for a lot of students. So we, of course, got to teach that explicitly. But there's the equation, and we got a whole poster on this too, if you really like this. But an equation emphasizes how both sides are equal. Calling it a mathematical model emphasizes how it models something in the real world. So we're explicit about teaching students that. And then obviously with proportional, when you double the input, the output doubles. So the choral response is some things in this world, when you double the input, the output doubles. You put twice as much gas in your car, you can drive twice as far. You work twice as many hours at your hourly job, you get twice the pay. If you're a teacher, if you work twice as many hours, unfortunately, that's horizontal line, and you get the same pay. So yes, But in this one, the core response, I'll do it. And then the hand motion, some things in this world, when you double the input, the output doubles, and then we tip. This one needs some work, but the students like this one, especially after horizontal line. You tip your arms to be the sloped line. But that one might get even better with time if you iterate that and would share, would be appreciated. But that one still is kind of we talked about changing it, and a lot of students were like, no. So that is, now how do we get students to be feeling really comfortable with proportional, which is a very intuitive pattern, right? They've seen proportional in their math and science. I'll just say a little bit more, and then I'll pass it off to Matt, but I'm going to close this. And we just have two different ramps that roll a ball on a floor. So we have a slow moving ball and a fast moving ball. So we call that jig sign. Just like a reading strategy is to have one student read chapter 1, one student read chapter 2, one student read chapter 3, and then they summarize to each other. We do that with the experimental setups. So one group has a low ramp to start their ball. One group has a high ramp. And now they have different data sets, and they can look to each other. Hey, you have a steep line and you had a steep ramp. Why? What about your steep ramp made that a steep line? And I might be going too deep here for the webinar, but that's a key insight. But the slope on this line is not the slope of the ramp, but it's a good insight. But what does the ball have when it's on the floor? Because it was started on a steep ramp. Oh, it has a higher speed or a higher velocity. Okay, but in any case, we jigsaw the experiments. And again, just like the inquiry cube, just like pendulum, there's a wild guess, and it's super fun. And we do it with a bowling ball if you want to maximize everything. So the question is, where will this bowling ball be when it's rolled down the ramp in 6 seconds? Students aren't allowed to collect data on up to 6 seconds. They only get to collect data up to like a couple seconds. So I'll close that and let Matt talk about that prediction.
Yeah, so this is just a good chance to make the learning visual, right? Experiential. We have students, half the class goes out, we do this out in the hall for us. We have them go out and stand at where their wild guess was. While the other half of students, they go out and they clump around where the data informed prediction is. And it's a time when you get some fist bumps on how close and how accurate this is. We have a video here because we don't have one of our in-person, just of showing this bowling ball rolling down. And we are able to kind of elicit using that data informed prediction versus that wild guess, and just getting that real visual that students know. Students are able to choose between the two jigsawed graphs that Bradford was showing earlier, and they choose which mathematical model to use. They're able to use that to help make their prediction. They use their graph and the math model to do that. And so really we aim to get students to use their resources, use their tools to make those predictions. That's really the culminating event. But one thing that we do kind of before that is have students, discuss this data. And Bradford, yeah, if you could close that. This is a new thing that was released over the summer here, and something that we've been doing a long time in our classroom is having data discussion scripts for overviewing and getting really all the good stuff that happens in a data discussion, and really scaffolding that and having students talking and working together to do that. And Bradford, I will hand that over to you to talk about that more.
Yeah. And my first concern is that you might see this and go, whoa, that is so detailed. And we really got pushed there from students and teachers that we used to have some cards that help students through a data discussion. Let me show you. So one, 12 years ago, we used to stand around whiteboards with the graphs on there and just talk in a circle. And that was pretty good, but a lot of students weren't participating. A lot of things got missed. So we had a graphic organizer, and that's this little thing, like put your two graphs here and find similarities and differences. Some questions about it, a card sort that we're going to show next time, and then make sense what that constant in the slope in the graph, it showed up as the slope of the line, the rate of change. In the model, it's a number. It was, well, we did show it 3.2. And then in the real world, it is the velocity. But we wanted students to fill these out, all of these boxes, and teachers, including myself, just said, like, students needed the teacher to say, what should I put here? And teachers had to run around. And we want it to be in small groups as much as possible, because if it's a whole class discussion, only one student talks at a time. So we really wanted to push it. And then that generated too many questions for the teacher. And at some point, it's always good to bring the whole class back and check in on things. But what makes that less likely to happen, or happen so many times, is really a script. And this is an early iteration, so super appreciate feedback. But in any case, this is really nice. I want to jump to that one where we need, so we have a placemat that you put on each table. So there's a student with A1, there's the next student next to them is A2, B3, B4. So they're a group of four. The first student would say, now we need to find similarities. The next student says, in terms of our experience or experimental setup, one similarity I saw was we both rolled balls down a ramp. And then the next student, regarding our graph, one similarity I saw was. So it is, this is not something you probably want to use all year. The minimum help to be successful, but those data discussions are some of the best things we do all year. Students are really in the role of scientists and making sense through talking to each other, student talk. So this, we're just, it got a lot of positive feedback. There's a lot of schools that have already started, and just really positive. They said, every student is talking. That's the first time they've had every student talking during a data discussion, maybe, and especially this early in the year. So students don't see this. This is kind of a lot. A student would only see what they're doing. So they have rounds and what they're talking about. So this is this overview for teachers. Good. All right. With that, those are all the little pieces in place to have students move through the graphic organizer so that they can talk about the different data sets. And the goal is that they really can make sense of that pattern largely independently, but this allows you to be the guide on the side. So you're walking around, checking in, answering questions, all that good stuff. I'll throw it to Matt to say that in one sense, we're only halfway through this lab. This is a very grounding lab, and hopefully you're seeing Unit 1 is much more than just the 4 experiments, or the 4 experiments ground a lot more than just the mathematical models. There's a lot of, being a scientist boot camp. With that, I'll let Matt talk about the confidence matrix.
Yeah, so we already talked in the webinar about our data-informed prediction at the end, but before we do that, we really want to discuss confidence. If you remember when we were talking about the inquiry cube, we talked about what happened to our confidence as we got more data. Well, we want to add some frameworks to that discussion. So we present them with data and ask them the question. That's a really valid question of, when does the data no longer become valid? When, as longer as the ball rolls, when is it going to, when are we going to have our data fall off? So Bradford, if you click on that next, go down a slide. So when does the model break down? And that's a really valid question. So it really depends on our best fit line of, what range does that data work in our data range? And keep on going, yeah. So we also talk about our data and how good is the data and how well does the data fit our best fit line. So we show them data and how would we describe it? Which data set would you have more confidence in? What would you consider and why? And then of course we have a visual that goes along with that in the determining the confidence in a prediction rubric. And so this gives them some visuals and to really start to have high level conversations about how confident are they in their prediction, be able to reference what they did in the experiment, how does that apply to the real world, and making those connections between their data and their prediction. The confidence rubric, this is one that it's on every lab, but we also post this and print this on our walls so that when we're making predictions, we can reference the data that is there. Yeah, I'll hand it back to Bradford.
Yeah. This one is really powerful, right? So many students, oftentimes, if you ask them what their confidence in a prediction is, it'll be like 100% because my calculator said that number, right? When you ask how far is that bowling ball going to be, 14.54, and they're 100% confident. Really, slow down, think about it. And every student will know this, that 6 seconds is pretty far. That's like 45 feet, right? So, oh my gosh, maybe friction is going to slow the ball down. So just want to say that this is building on some intuition that students have. And yeah, I was going to try to ask a question, but it's always difficult in this format. What else can you imagine students might come up with? If it's 45 feet and they don't know you're going into the hallway, it could just straight hit a wall and it's no longer going to keep moving forward like the mathematical model predicts. Anyways, that's that bottom one. And one last little piece about this. This is great when students ask about a video they saw or a claim by, again, like different videos or politicians and stuff. They make claims. You can ask or advertisements, right? Like advertisements make some pretty serious claims and then they present, an advertisement in the guise of data. But anyways, this is something that a lot of teachers have talked about referring back to with students. Okay, how much confidence should we have in this prediction that was just brought up? Right.
Yeah, so at the end, students are, again, working with these science concepts that are new to them. And we just have another way to get them to interact with a conclusion that's not writing the whole conclusion. So you saw in the first lab, it was kind of fill in the blank. This is another way. And we're not going to show you the activity itself, but they do a conclusion sort, a sentence sort. So they are given 3 claims: low quality, medium quality, high quality, 3 evidence pieces, math model, prediction, and confidence. And then they're asked to analyze and sort. If it's not printed in color, they can analyze, is the sentence making a claim or is it a mathematical model with reasoning? What is that? And then they sort them from that high, medium, low quality. And in our classes, they take a picture and they use that as an exemplar for the next experiment to look at and assess. So it's just another way for us to interact with information, for us to interact with each other, and to allow students to get another exposure at a conclusion.
Yep, so nice. And that's a reaction to, not wanting to overwhelm students, but wanting them to be thinking, how do we go from data to a graph to conclusions? And one last piece of that is, especially as students are beginning to write conclusions, the writing is the hardest part. And sometimes we want them to access the high level aspect of a conclusion. We want them to see good conclusions. And if a student is struggling to write one, and the only way we access them seeing good conclusions is to have them write it, that can be a long journey. But here we're starting with, as we so often do, Desmos does a lot of work to making graphs quickly so students can access high level thinking, mathematical thinking, instead of just making every graph by hand. Here, the same thing with writing. Let them spend if you only got 20 minutes to spend on the conclusion, you could spend it on them writing, and they might not even write everything. Or we could have 20 minutes where they're talking. Hey, what made this high quality claim better than the medium quality is this and that. So anyways, just time on task. And the task we wanted to focus on here was what makes a good conclusion. And of course, you could just see that in the previous slide.
Bradford, can you go to the teacher calendar really quick? Just wanted to maybe it's give you an overview of like kind of where we're at and what task we're in. So first task we mentioned was inquiry cube. The second task, as he scrolls down, we have the pendulum experiment, and that third task there, that ball on floor experiment. There's one small piece that we haven't discussed within that, and that is our introduction to claim evidence reasoning. So we do that, we transition to that with a non-science example of a cat walking down the stairs. So this is in the packet, and if you could scroll to page 6. Students construct an argument, and maybe zoom in on the cat, Bradford, please. Students construct an argument from this picture, and we intentionally chose a non-science example to introduce claim evidence reasoning so that students are eager and excited to participate, but also using the picture and some people their own evidence of, is this cat? And we wanted this low stakes. We wanted students to be able to come up with an argument as they were doing that. So if you zoom back out, there's a graphic organizer that goes along with that to teach, and some slides, which we're not going to show at this time, but looking at the claim, and we introduce the idea of claim. Looking at the evidence, we introduce that idea of evidence and connecting that to the reasoning, how the evidence backs up the claim, showing that reasoning. So that's an activity that we do to introduce that, and you'll see like later on in quizzes, assessments, other times students are writing claim evidence reasonings as they are interacting with ideas. So and I think I will hand it back to Bradford to talk about our third anchoring experiment.
And I'll quick give just an example. Students pay attention to what's going on with the tail, the shadows here. It's a lively, it's meant to be low stakes, exposure, practice, mastery. The inquiry cube is a real easy first touch. Hopefully you're seeing so many things more than just the mathematical model spiral in this course. So we always have a easy first approach to each of the big things that we want students to do. Okay, another big piece of the puzzle is, we do this so often in science that when you want to study something, lots of times you don't fully take on studying the exact thing. And I'll just pick a reference to Unit 4. In Unit 4, it's around engineering a shoe. And we have footage of shoe designers, and they want to study athletes. It's very hard to study athletes in the middle of a game. So what do? They put the athlete on a treadmill so that they can control all the different features. So, or they have them make basketball moves, not in the middle of a game, but just on a floor where they can put scales on the basketball court and see the pressure that a basketball player makes when they make a cut. And so they need them to step on the scale that's only like 1 foot by 1 foot. So in any case, analogous system of study. That's one of a vocab word that we want to explicitly teach students. So this one is under the guise of looking at packing food, and it could be a light touch of 30 seconds, maybe it's 5 minutes, depending on how much you want to go into it. That is not our prize as physics teachers, but it adds context. It connects what we're doing in class to the real world. And in any case, this is real, that the more efficient packing of food reduces the carbon footprint of transportation. And that can be significant with many food items, packing it more efficiently. So in any case, they're asked to wild guess predict about, well, actually, I was just going to show a couple slides. So we don't want to study tomatoes. That would be wasteful to really use tomatoes for this experiment. So we, in our analogous system of study, we're going to use a different system. Here's that, vocab wall, analogous system of study. We're going to use a different system that's often easier to study, but has the same pattern. So packing metal ball bearings will give the same pattern as packing real tomatoes, and it's far less wasteful to use real tomatoes. But anyways, so we switch over to the ball bearings, and the question is just really, how many will fit in this diameter of a circle? It's very intentional. Actually, I'll try to finish this one because I knew a couple of these were coming. So how does the diameter of a circle affect the number of marbles or tomatoes, depending on how much you want to play the tomato angle, fit within it? Okay, and then students collect data in a data table. I'm not going to show every step. And this is where we decided to show Desmos. So this will be, that's funny. This is an old one, but I'll quick get that changed. Okay. And this is the answer key. So it's missing. And I'm just thinking I'm thinking probably people have seen this, but they would also have, we pulled up the answer keys. We just want to focus on it. But if you haven't seen it, and I wish I would have changed the color on that. There we go. So students they see all four models every time. And I could get this straight line. If I get the first point, it misses the later points. If I go up and get the last, now I missed the other one. So students visually see proportional just doesn't work. And they know it's a positive relationship. Okay, so I'm going to get rid of it. And they quickly see the only pattern that's going to work is this one. And for most students, it's the first time they've seen quadratic. And it goes really well. So that's what we hope it goes really well. And we do a lot of steps to try to make it. So they don't understand it right yet, but they get the equation M. And I strongly suggest this is a move that a lot of teachers have reported positive experience. Yes, Desmos makes us abbreviate M equals CD squared. Strongly suggest having you write it out. A lot of experts shorten things, right? So if I say the NGSS, the PEs and the SEPs and the CCCs and the NGSS, whoa, we make fun of people that do that all the time. But we as physics teachers are doing that a lot with equations. And so we, just think of the student that was absent or a student that's struggling. They see M equals CD. What's C? Oh, it's 0.5. Well, why don't you just say 0.5 instead of C? So it's just think about it. Marbles equals 0.5. And this is another one. Lots of students get messed up with that 2 squared. We know that it's 2 squared. Lots of times they just multiply by 2. So let's help them out. And just on this equation right here, we actually have them write diameter times diameter. And that is a good thing. Conceptually, that is how you should think about it. Now, it's painful to write out diameter times diameter a bunch of times, so it's totally understandable why everyone shortens it to D squared. But the first time or a couple times, it's really useful to write out diameter times diameter. Why? Especially, why is there diameter in there twice? And if you're willing to play along, I'm going to stop the screen share to show, oh my goodness, I need a second. So I'm going to throw it back to Matt and I'll get our prop set up.
Yeah, so students, this is the first time that they've been exposed to seeing a quadratic, and many of our students see this and they say exponential. We explicitly want to compare and contrast those. So there are some slides in the slide deck to elicit that and help that. But we want students to start to get that tangible feel for what does quadratic mean? Like, why do we call it quadratic? And really be able to use that mathematical modeling to connect the graph, the equation, and the experience. So this is one that Bradford mentioned earlier, that other groups, before they do their data discussion, other groups have also done this with other sized marbles or ball bearings. And that allows a real reason for students to check in and chat with each other. Small marbles are going to give a different rate of change or curvature. They're going to give a different value. And those two things, those combined, allow students to really try to analyze and figure out, what does that constant mean? So there's a variety of resources that go along to support that. In a bit, we'll show card sorts, we have our scripts, as well as looking at the graphic organizer for the data discussions as well.
Yeah. So perfect. And just to show, we are going to now show the card sorts. So again, they would have only studied 2 of these. So everyone gets introduced to a new card sort, and these are all mixed up, so they're not in order, even for you. So that's just sometimes, if you have, anyways, you just cut these all up and students need to sort them out. So I'll say, actually, if you haven't thought about it, almost everyone gets this wrong, including me. You think large marble, and your intuition is to connect it to the large number and the graph that is strongly going up, but it's actually the opposite. And so the small marble has the big number. So what does a small marble? This is a question we always ask, or this is a teacher move in this discussion. In terms of packing, what does a small marble have more of? We always try to say it in the positive. So what does a small marble have more of than a big one in terms of packing? And I'll just, since it's webinar, we'll just kind of march forward. It's more packable. It's more, and we like words of understanding before technical. But remember, we like to say everything multiple times, multiple ways. One of them should always be technical, but it probably is not the first one said. So more packable, more packiness, more, that's all I can think of right now. But okay, so they see that a smaller marble is more packable, and it's right here. And so often we want to put in lots of different numbers, but 2 is the go-to for the choral response, but we could put in 3, 4, 5 if you want to practice this a couple times. So let's just quick look on the graph though. If I go from 4 and double it to 8, well, let's just look at 4. Oh, I'm grabbing the point, unfortunately. I'm going to move the point away. And 4, at 4, 8 or 7 or 8 marbles fit in. If I get right to 4, I don't know what it is. 8. I'm stuck where I don't want to be. 8, or sorry, at 4 diameter, 8 fit. If I double the size from 4 to 8, what does the number do? Move that so I can click on the actual line. It quadruples. It quadruples. Okay, and let's check that. If I double the diameter, so I'm doubling the diameter. So the diameter, I'm going to sneak a 2 in here. This is a me thing, and not everyone likes that 2 idea. But if I make the diameter twice, I got to put it in 2 times. So if the diameter gets twice as big, what happens to the right side of the equation? It gets 4 times as big. So what does the left side have to do to stay equal? 4. So doubling the input makes the output quadruple. And of course, we have the little, you would have pictures in class of that. And I'm going to go just to the punchline here. So I'm going to do the choral response. So this is, I want to say that this is how we get students who have never seen quadratic before. By the end of this lab, they have lived the experience. They see it in the experience, they see it on the graph. That's what I tried to show on the graph. And then they see it in the mathematical model. And afterwards, how do we like this as an anchoring experiment? Because at the end, the mantra is some things in this world, and I'm I think my virtual background might work against me, so we'll try to make this work. Some things in this world, when you double the input, this is not the core response, I'm just gonna say it long-winded once. Some things in this world, when you double the input, it doesn't stay the same. It doesn't double. Two things happen. When you double the diameter, two things happen. That thing gets twice as wide and twice as tall. So the output quadruples. What's a good name for that pattern? Quadratic. And that is powerful. It can be a week later, it could be almost a month later. I bet after this experiment, again, this is like a 2-day thing, and we were doing it in like 20 minutes, that yes, some things in this world, like packing tomatoes in a circle, when you double the diameter, it's twice as wide and twice as tall. This was the one, and it's meant to be fun. I really don't know how this is going to go on the webinar, but we were hoping that if a couple people, it's going to be messy, but just to have a little bit of interaction. We're about to go into a breakout room too. Well, this is our test here. If you're willing to unmute, I'll one-time practice, and then we'll just see if a couple people want to join in. So this one does have a little more choreography. So it's some things in this world, when you double the input, two, and that little two, shaking two things happen. Twice as wide, twice as tall, so the output quadruples. We hold up 4. So if you're willing to unmute, we're gonna try this. In 3, 2, 1. Some things in this
world,
when you double the
input,
two
things happen.
It gets twice as wide.
It gets twice as tall.
So the output quadruples. We call that pattern quadratic. All right, thank you. And it is more fun. Definitely was more fun for me to just have that. And I'll just say, people are at different places. Some teachers right away, they see that and they love it, and they just can't wait to do it with their students. Some are on the fence. If you're on the fence, strongly encourage you to try it. And if it's not your thing, it's not your thing. So no worries on that. Okay, so we got those choral responses, and isn't it nice? At the end of the day, students really get why it's quadratic. Why did doubling the input make the output quadruple? And again, I'm going to go back to share screen, and I'm about to hand it off to Matt, and we're getting close on the breakout room. So, all right, but just want to say, it's not enough to just say that one time. After you say it, you got to go back and show the graph and show the mathematical model. We want them connecting it. And you might do that with tripling. Hey, if I put a 3 in here, if the diameter gets 3 times bigger, and of course you have some rings from class, you could show this with the marbles. So if the diameter gets 3 times bigger, 3 times 3, oh, that's 9, the 9 times as many marbles. And we could go to the graph and check it. If it went from 4, 8, 12. Okay, what was it at 4? It was, I'm going too long on this. So it gets 9 times bigger, 9 times 8, 72. Yeah, there we go. So when you triple the diameter, the output gets 9 times bigger. Just want to show there's 10 minutes of group talk after the data discussion to just go through and show. We call this walk the triangle. Show in real life. Show a ring that's 4 and a ring with 12. Then show in the mathematical model why tripling, and then show on the graph that it's tripling. All right, so Matt's going to give us the last touch on showing the progression with conclusions, and then we have our first breakout room prompt. So I'll throw it over to Matt.
Yeah, so thanks, Bedford. So we wanted to just really have you get a glimpse of that overarching conclusion. And so we've talked about that a couple of times. This is another one. And Bedford, if you go up one slide, actually just wanted to note that there are some slides that are green, and green slides are always teacher notes, something that might be coming up. In this case, we are using what we call the roving conclusion activity. They are meant to get students a shot at writing and then checking their writing with somebody else. So, Bradford, if you could go to that next slide for me, please. They're given a sentence starter. They write their claim after investigating packing behavior of marbles. I conclude there is a quadratic relationship between the diameter and the number of marbles that fit. Once they have written their claim, they're going to go to somebody else in the class. We play music, and then when we stop the music, the person who's close to them, and then they read their claim and try to incorporate and make it better. Then we go on to the next part, the evidence section. Give some evidence, some sentence starters for them, and again we repeat: play some music, walk around, let them stop next to somebody and share their evidence. So this is just another way, a social way to write, gets them another shot at a conclusion, gets them to look at, and allows them just to be able to interact with somebody as they're writing their conclusion in preparation to write on their own. So it's a social way to do that. Good. And yeah, so we planned, and if you go back to the agenda, Bradford, really that's our wrap up from our third anchoring pattern, but we wanted to give you some time to discuss, and I actually have it in the chat, Bradford, I got it. I put some links in my message, and I know some people who don't have the new Zoom model might not be able to access the links, but the question is, what level of support would you use for a data discussion? Would you use or have you used? And we're gonna put you in breakout rooms of they're 3 to 4, I believe. And we just want to give you some time to be able to interact with each other, maybe introduce yourself, say the context that you're in, and then really dig into what supports have you used in the past in data discussions. We realize that when you go into a breakout room, sometimes the prompt goes away. So we will maybe put that in a message above. But again, what level of support will you use or do you use in data discussions? Bradford, what's a good time, do you think?
Yeah, we want to balance it. Yeah, maybe I think like 7 minutes.
Yeah, let's do that. So I'm gonna set it to automatically close after 7 minutes. And we will jump into some breakout rooms here. Feel free to call Bradford and I into one if you want. Right. We will see you here in a little bit. Again, your prompt is there in the chat.
And we did enable screen share if you somehow wanted to share your screen to talk about stuff.
Six.
We're gonna check the parking lots.
Bradford, do you know the answer to that top one?
On the self-assessment?
On the peer review, yeah.
On the, oh wait, I think I just see how our self-assessments on the front of each packet used.
Nope, that's a different one. I'll put it in the chat. That's different than the one I was linking.
I only see one on there. That's why I was wondering.
Look in the chat right now. I just posted it.
Yeah.
They were asking about the equip peer review panel.
Oh, equip. I don't, oh, whoa, is this a different? Wow, I must be in a different, video capture tool. I'm gonna close that. It wasn't, yeah, I did wonder, okay. Yeah, cool, I'm there, all right. Ooh, yeah.
Oh, issues. Oh, no, no problem, Carrie. I let's see. Not a big deal. I don't know if I can send you back to that room or if you just want to hang out. We have just 4 minutes and 30 seconds left. So. Hmm. I'll get zero supply for the next one, Bradford.
What is the stamp called? The next gen science,
Yeah. I don't remember.
Susan, are you here?
I'm here.
What's the next gen stamp of approval called?
NGSS badge.
Yes.
Hmm.
Okay, we have about 2 minutes here, Bradford.
Yeah. Okay. Is the rural PLC? Is that for sure happening? Is it worth just?
Yeah, it's in the flyer. It's happening, I think, let's see here. Yeah, rural teacher focus group. I don't know if the PLC is happening.
Okay.
I'm trying to convince Casey to run one. So, but I haven't had success so far. But we can certainly tell them are people expressing an interest in that?
Yeah.
Yeah, and they did in the feedback and the summer workshops as well. Maybe I'll send him an email right now.
I want to get the Good, it's good. Although one slide I didn't see. Oh yeah, it's probably this one. Okay.
All right. Maybe share your screen. They're going to come back in 20 seconds here.
Yeah.
By any chance, did you pause the recording during the breakout?
I just realized that I did not.
Next time, if you do a breakout, do that.
Yes.
Bradford and I never remember as well, but
I went, oh.
You, yeah, in like 5 seconds. Hold on.
Yeah, they're coming back now.
Yeah. Hello, welcome back. Excellent. Maybe worth starting back at the agenda. So we're just going to talk about the last anchor experience and some really important activities to make sure students are seeing the big ideas a little bit of, and then back into another breakout room, and then wrap up with the assessment opportunities. So jumping just as a closure on the quadratic, want to just show that poster. So have a poster, and these are strongly encouraged if you are able to print them, is even if they're just really small, you know, just the 8.5 by 11, or if you have the capabilities to print or have a small budget for your department, to have those hanging up in your room. We have a picture of that set up, although it's in the slide deck that I closed. Nice. Okay, so also students on the front page of the packet, they're drawing that picture in, following that storyline. And again, what's the storyline for this first unit? Is how do we find and use patterns in nature to predict the future, make data-informed decisions in the present, and understand the past? It's worth saying, actually, in every other unit, there is an engineering project that follows the storyline. But that was just one more thing that's just too much in Unit 1. Hopefully you're seeing there's a lot going on in Unit 1. And as soon as we're really feel that we're at that limit of, if you do one more thing here, something else pops out. So with that said, though, that wraps up our third anchoring experience. We had horizontal line, proportional, and quadratic. And then I'll throw it over to Matt to talk about the fourth experience that students get in Unit 1.
Yeah, so in the fourth experience, students are given they're asking questions kind of in another system that is made by people, which is, you know, looking at paragraphs. This is something that came out of conversations that we had with OSU engineering professor, and people often ask, you know, why are we going to paragraphs? Well, this is a really great anchoring experience for our students to come back to over and over again through the year. It gets some really physical, connecting that physical to the graph, to the math model. So trying to find it up here on my slide as well. We present them with, again, a wild guess question. And the question is, what is the height of this paragraph that I'm about to read when it is printed 30 centimeters wide? And so the paragraph that we read is, science is finding patterns in nature and using those patterns to accurately predict the future. For instance, one pattern in nature that nearly everyone has discovered is that objects on Earth, when unsupported, fall. And we have named this pattern gravity. We can predict tomorrow that if you were to hold up a marker and let it go, that marker would fall to the floor. Now, scientists and engineers have discovered many patterns and gone as far as creating a device from materials found in the Earth's crust that if tomorrow you touch it in a certain way and talk towards it, a loved one can hear your voice miles away. We of course call that amazing combination of stuff from the ground a cell phone. So we start with that, and we have students look and make their wild guess about that, and then we want them to, that kind of meditates the controls and things like that. With that, I might hand it over to Bradford.
Yeah, and I just want to harp on that last point. We want to show how intuitive. A student will ask, well, what font is it? What spacing do you have? And that is why we always like starting with these wild guesses. That shows that students start doing the process of science. Everything they list is either a variable or a control. So by the nature of asking this question first, students go into the data section and they actually have some thoughts. If a student lands at controls and hasn't thought about controls yet, that is really difficult for most students to come up with what they need to control. But with the wild guess question, they've already done it for the most part. What is the font? What's the spacing? All that good stuff. Okay, and then this one is really nice. And Matt said it, and I'll say it too, because sometimes we've just gotten this pushback until people try it. Almost everyone after they tried it has come around, and always want to remain open to new ones. But paragraphs really have this nice thing, multiple nice things about it, and this is one of them. If you take like there's 5 paragraphs, we print them on paper and they cut them out, and you put it on the graph, you literally get all 3 representations together. If you put the bottom left, corner at the origin, the width of the paragraph is just literally the width. It shows you if that's 6 centimeters wide, it will be 6 centimeters wide. And so the data point for it literally is the upper right corner of the paragraph. That is so tangible for students. And students of different math abilities, every student gets this. We call this low floor, high ceiling. Every student gets, even though they haven't seen inversely proportional in math class for many students. It just totally makes sense. And I would just say again, the big pattern makes sense. Yeah, no surprise. The only confusion students have is they think it's words when it turns out to be the area, right? If you move a word over, it's going to get shorter. They all know that. And we have this, I want to come back to this graph, but I just want to show that. We actually think it does better on paper, even though you can do a live action. We've done the live action, but paper is really nice, especially so that they can make that one-to-one paragraph. But if I double the width, no surprise, it gets shorter, half the width. So I want to go back to that graph though, because it's just so powerful. There's no student that's like, I'm so confused. Maybe that's too big of a statement, but I would say almost every student is like, okay. And if you have big font, and of course, why do we have the same paragraph with bigger font? So that when students say it's the number of words, you can say, no, the purple paragraph has the same words. Why is their line higher? Every kid can say it. Yeah, their words are bigger, so their corner gets pushed up. It totally makes sense. And then questions like, why is it asymptotic? Big fancy word, asymptote. But every student can answer that. If it's a real paragraph, it has to have some height. So these things that are sometimes difficult when presented in the context of like acceleration equals force divided by mass, this first early exposure, this is the cat going down or up the stairs version of inversely proportional. So again, we could walk the triangle. If you make the width twice as big, this one is a fan favorite by students and even teachers. So let's do that one time. If you have a piece of paper around you, I encourage you to grab it because it is such and raid your recycle bin before. Thank you for that, I'm sure. Every student likes this. And of course they have those little paragraphs, so they can do it with a real paragraph in front of them, but then we just switch over to paper. It's just so easy to grab, but it is so intuitive. That is why I'm going to start with a smaller piece of paper, but I'm going to start from the top, which is so fun. If you're into the choral response and your students are too, some things in this world, when you double the input, the output stays the same. And swing that pendulum again, leave that pendulum up for the whole unit 1. I actually leave it up for the whole year. I just clip it with a carabiner a little bit high up. Then some things in this world, get out that bowling ball, roll it twice the time, it goes twice as far. Some things in this world, always have your little piece of quadratic paper around. When you double the input, two things happen. It gets twice as wide, it gets twice as tall. So the output quadruples, we call it quadratic. And now I'm not going to do the choral one lead. I'll just say the long-winded version. Some things in this world are totally different. When you make the input bigger, the output gets smaller. And in fact, this one gets smaller in a very particular way. And I'll jump for dramatic effect and talk about IB physics students. They know about exponential decay, and they sometimes mix up exponential decay and inversely proportional. And you got to pull that graph up. Matt mentioned it. Lots of freshmen mix up quadratic and exponential. They think as soon as they see something up curvy, they think quadratic and exponential are synonyms. And anyways, I don't want to get dragged into that. So some things in this world, when you make, okay, we have changed the choral response because we like to emphasize the twice and twice. But it doesn't matter. You like it one way, do it the other. So I'm going to say the choral response. Some things in this world, when you make the input twice as big, that's the width of paper. When you make the input twice as big, the output gets twice as small. And we do this hand motion. So they are proportional. If I make this 4 times as wide, it has to get 4 times. Someone asked for a pro tip. Pro tip, if you learn how to rip it, and I half the time get it right, half the time get it wrong, you can do all 4 though. So some things in this world, when you make it 4 times wider, it gets 4 times smaller. That's proportional, 4 and 4, 2 and 2. If I made this 8 times wider, it would get 8 times shorter. So it's proportional, but it's opposites. So we do the opposites with our hands, and the technical term is inversely. So the choral response is, I'll get a new sheet of paper. That's again, so why it's so valuable. Some things in this world, when the input gets twice as big, the output gets twice as small. That's it. And you rip that paper, so powerful. I'll just say that, think, this comes up with acceleration equals force divided by mass. This comes up with the wave equation. Wave, I'm trying to think which way do we say it? Wavelength equals, they don't know it when they first do the experiment, but wave velocity divided by frequency. And this, we have, inversely proportional doesn't come that often. It might be like a month between instances of it, but you get out paper, every student right away knows the mathematical thinking with inversely proportional. Yes, it's proportional and inverse. It has to be. There's a constant amount of paper, so it's either on the bottom or it's on the side. Okay, I'll cut myself off there. So that is the idea, though. That is the anchoring experience with paragraphs. And I'll just hark back to so much good stuff with the triangle. They learn way more than just that. That is the mission critical piece, though. Twice the input, twice as small, but we get a lot of students, and encourage you to try to get a lot of your students talking a lot of different properties of the inversely proportional curve. And that's, someone asked, how do you do this with multiple grade levels in the same room? We call this built-in differentiation. You don't have to bring up asymptotes, but if students bring it up, yes, it's a very rich discussion that can be grounded in a way that students can engage with. But that's not the mission critical. We want mission critical is the inversely proportional nature of that. And we're about to go into the review, so I'll just say this one time while we have it right in front of us. We've made a math equation that behaves the same as paragraphs in the real world. That last one with marbles, we made a mathematical model, a mathematical equation, but we're going to call it mathematical model because, I know I'm going to say this one more time, and I'm going to grab my globe. So I'm going to throw it over to Matt to wrap up our 4th anchoring experiment. And then I'll say what I was going to say, actually, in terms of the review day.
Sorry, it was muted. Can you hit to that next slide, Bradford?
Yep.
Sorry, the next tab.
Next one over, yep. I got this Zoom thing is in my way. Okay. There we go.
One more.
Yep.
Yeah, so this is opportunity. Again, we established this on day one. The most important things need to be said multiple times in multiple ways. So we really want students to be able to connect, the graph to the experience to the mathematical model, mathematical model to the graph. And so this is a poster that's up in our room, oftentimes for me, that I want students to say things out multiple times, multiple ways. And maybe that one new understanding really helps that stick. If you could, Bradford, go one more over. To stay on the same theme and then scroll all the way down to the bottom of paragraph. To stay on that same theme of giving students leveled supports for writing. If you look there, and if you could zoom in a little bit, Bradford, there are multiple layers of supports that allow students to access this. So first, data discussion card sorts, add some structure, but then there's level 0 support all the way up to conclusion. So level 0, we say like that's something that everyone gets at the bottom of a conclusion. It has the parts of the conclusion written out, kind of a little checklist of all the things that it needs. That's that first level of support. And then maybe we don't go through all of them, but let's just show the level 2 support. Another layer of a support is a self-assessment checklist. So do they have all those pieces? And it has some sentence stems in there that allows them to access that. If you scroll down all the way to the bottom, there's the other sections that are there too, that allow them to access giving different supports. Now, we don't give all of these supports to every student. We, of course, are trying to always give the least amount of support possible to allow students to access that success. And then, so there's all these levels of support that we can give to students and to allow them to access writing those conclusions. Yeah.
And maybe we're saying, so this would be the first time we suggest putting the lab report in the grade book. So all of that was exposure, practice, mastery. Now that we've done 4, and again, that arc was fill in the blank with teacher help. Then it was take 3 pre-made conclusions, all scrambled up each sentence, and talk about what's a claim, what's evidence, what's a good claim, what's a medium claim. Then that last one was the roving paragraph where they're writing, but getting to connect with another student and revise. And now here, we are expecting mastery. We do want to possibly give a summative assessment, give them grade and a feedback on how they're doing on writing that up. So we're about to zoom out. I'm just going to go to the agenda quick to show it. All right, so we've sort of wrapped up the paragraph lab. And now there's a lot of big ideas. And really, we hope the living the experience is enough. But it's worth bringing some closure. And we're actually going to have you in your breakout room do one. But I want to show one poster. I don't know if you want to show this to students or not. That mathematical model is a new word to students. And I do want to, for anyone that's new, I know this is not new to a lot of people. Try to do that spotlight. So if, mathematical model is very emphasized in the NGSS, most models that students are used to look like the object, like a globe. And of course, it's very nice to have a globe. Again, there's a lot to say about it, but I'll stay on target and just talk about, we are making something, not a globe, we're making a math equation act like our system. And so just to repeat, if you make the width twice as big in that math equation, it makes the width in the math equation get twice as small. And that models what happens to the real paragraph. It also models what happens on the graph. This might be a nice poster to have up if students are really struggling with it. We find that just they need to see math models a few times. There's just no way to, that's what we say, exposure, practice, mastery. That doesn't, if they call it a math equation, that's totally fine. We do actually want them to appreciate, though, that we are making an equation that acts like the physical system. We're making a model of it. Okay, with that, we want to show you, oh yeah, here's our poster.
You gotta share.
Oh yeah, I'm not sharing. I do that. Sorry about that. Here's the poster for inverse. Oh, did I wait? Was I not sharing when I showed the math? Oh,
Showed it for a second and then it went away.
Okay, shoot. Okay, sorry about that. All right, well, here is the poster for inversely proportional to wrap that up. And then on the review day, you saw it we started off this webinar with it. One of the biggest ideas, and most students, lots of times I do a fist to 5 check on this a couple times in the unit. Yeah, this, there's a lot of big words here, but students really get to feel this after experiment after experiment after experiment. Yeah, we study something, collect data, explore the patterns, that mathematical equation to better understand the system and influence its future behavior. All right, so we're about to show you what you're going to do in the breakout room to start, and we're going to have a little bit longer breakout room. We ask, lots of times people like to do the thing, complete it, and then, yep, with that extra time, just check in. There's a lot in today, and, just looking at the participant list, there's a lot of experience in the room. So I know people have, there's a lot of people that have taught this, and, it's great to hear how their experience has been, and obviously just talking. This is a network of teachers. So, okay, so what is that big activity? Let's look at these posters. And if you're going to hang posters up, these are the 4 mathematical models are really critical. And then the essential question, if you only have 5, that would be it. The essential question and the 4 models. But if you have the ability to print, and even in black and white, just having these other ones around, I'm not going to say too much more about them, because that's what we want you to say, and that's what we want students to say. And so I'll put up the directions. And so each group, if in your breakout room, if you would just select a poster and just discuss what's the big idea in the poster, why did we make it into a poster, what was special about it, and how does that help? How does that poster connect or help us with the biggest idea we just discussed? And of course, here's a little version of it. And then you're just going to take turns. And again, we sometimes you say take turns and then no one starts. That's why we just have the A1. They know exactly who should start. And that helps. That doesn't always help. Sometimes A1 doesn't want to go, but it helps 3 groups. And then you're just talking to the one group that hasn't started yet. So those are just some nice little features built in to the curriculum to help students get talking. So I'm going to hand it over to Matt to repeat the instructions and make sure I didn't miss anything. Sometimes it's just helpful to hear it a second time. Even in class, you might even get a student to repeat the instructions. With that, though, I'll throw it over to Matt.
Yeah, thanks, Bradford. So in the chat, I just put the link to that. I put it twice because first one is for people who have the newer Zoom. It says first try out the student review activity. So it's going to link you to the posters. And you will choose a poster and go to the next slide and just talk about what is the big idea that your poster embodies and how does that poster connect us or help us with the biggest idea in physics, which is listed on that page. And then after you have discussed your poster, discuss the value of making these big ideas so explicit with students. We probably do 8-minute breakout room, Bradford, do you think? Just checking
Yep.
the time.
Yep.
Yeah. And you'll be in the same breakout rooms with the exception of one group. A couple people dropped, so that you might have a new person added to your group. And so we'll open those up for 8 minutes and we will see you when you get back. Thanks, everybody. Welcome back, everybody. We'll just wait till everyone gets back in here. And I gotta hit. Yeah, so we've heard in the past that it's just nice to connect with other educators and use those breakout rooms. So we hope that was valuable time for you. We wanted to finish off here by looking at some assessments that we have for the units. And we intentionally didn't want to integrate these throughout, just for the whiplash of kind of going in and out of there. So we have many different forms of assessment here. And just to start with the quizzes, we really model guide step aside this exposing them to a format. We really wanted a similar format throughout here. So Bradford, if you could click on 1Q1 there, please, the quiz on proportional. So the quizzes are related to the experiments that they did. So you can see the format. They are given some data for a ball rolling on the floor. They're asked to make some predictions for the different math models or using the graph. And then ultimately they are asked to give their confidence and write claim evidence reasoning format of what the difference, which marble is faster and how they knew. So they're asked to do some writing, and then hopefully when you see, go ahead and click on that next one, Bradford, a very similar format. They're asked now about the marble packing experiment. They're given some data. They're asked to predict, and also predict with using reasoning what happens. And then again, in the claim evidence reasoning format, giving a explanation for what is different, which marble is larger or smaller. In the final quiz here, it's on the proportional pattern, and really, again, similar format, asking a prediction, confidence, and then getting students to write about their reasoning in that claim evidence reasoning format. So predictable patterns of these that allow them to show that growth, and using the same sort of format for each of these. Bradford, if you want to talk about the last questions here and the patterns in your life.
Yeah. So just that option, there is a, oops, close that out. There is a test, but we've just found that test for lots of times it derails the unit and the intention. Teachers have a couple days of review, they take the test and they're overwhelmed, and then there's a day of reteaching and retaking, and all of a sudden unit 1, which is this exposure unit, it's meant to be just 3 weeks, 4 weeks long, and all of a sudden it turns 5 weeks, 6 weeks. And I haven't said this yet, but we really want to get to unit 6. That is the unit we teach electric guitars and climate change. You really want to get to unit 6. You don't want unit 1 to puff up. And it really is, they don't have to master quadratic and inversely proportional. They need to know some things are quadratic, double the time that, or sorry, I said time, but diameter, 2 things happen. And that's good because the next experiment is going to be acceleration. 1/2 AT squared. Why is time in there twice? Because two things happen when you roll a ball. I'm now talking about a lab we haven't shown, but if you roll a ball down a ramp and accelerates, two things happen. It has twice the time to roll, and like the bowling ball, twice the time, it goes twice as far. But this, on down a ramp, it's accelerating. So it's twice the time to roll and twice the time to speed up. Yes, in our mathematical model, time should be in there twice. So, whoa, I was guilty of, I went on a pretty long stream there. So we really don't want, they will get quadratic in the next unit. So that is exposure, practice, mastery. So this test is there. We actually almost want to say discourage it, but there are people that do really want that test. And so we have it and want to provide that resource, but do encourage you to consider doing the 3 quizzes. And with that quiz, then there is a couple extra questions on that 3rd quiz. So it's about proportional, some of the other big ideas, and just explain, why do we prefer a data-informed decision over a wild guess? And that's surprisingly hard to write in a sentence. And we, of course, want students to be able to do that by the end of this unit. And compare and contrast proportional and inversely proportional. Include rate of change. Your math teachers will be really excited. And then we didn't want more writing, but we really wanted them to connect the big idea of physics with the parts of our experiments. And so it's a matching task, really easy. And you really got to do thinking, but it is a matching task. So it's just a little more achievable and not just right. Okay, excellent. And then to zoom out, what do we really want? We want students taking patterns and connecting it to their life. We wanted them taking this scientific mindset and bringing it to their life. And so that's what better to do than to actually ask them just to do that. And so what are some things in your own personal life that you might look for patterns with? How much time you are on social media comes up again and again. How much sleep you get. What kind of things energize you versus kind of suck your energy away. And then they don't have to do it, but we need them practicing this. They will design their own experiments, but they need some reps before. Lots of times, most students can't design a good experiment. So this is that baby step. All right, choose one of these. And just think, how would you collect data? And then I know I got to keep this short, so I'll say, then we do the same thing at the community level and the worldwide level. And they're just brainstorming questions. Come up with questions, think about how you might collect data. I'll just quickly say that, there's a really great resource on what's going on in this graph. And that's the New York Times has a math teacher, and they go and pull out informational graphics, all throughout the news, and then create little mini lessons. But here's a chance to bring up inequality, social justice, environmental justice in this patterns in your life. Students might be interested in that. So you just got to look at each one. I don't know, there's 28 in here, but I don't want to get sucked in too much, but that is great. And that is what most teachers go with. And then there's just a question on some reflection. And this is, I think, one of the best things we do. It's a little bit hard to grade, but there's a rubric here that actually makes that very fast. This is a low floor, high ceiling. I would just say that this is meant to be 1 or 2 days in class, and students can get the full range of grades in that 1 or 2 days. And some students do things that are just amazing. I was trying to think if we put the exemplars in there, but sometimes if you show amazing, then everyone feels like every student's supposed to do that. So in any case, it's just really nice to see what some students do, but again, students need support. Asking questions is really challenging. So that is, though, an alternative way of really building on the intentionality of this unit and connecting their science education to their real life. There's a nice pinhole camera that's an extension. Some people ask for that. If you have like an honors requirement, or some students need more time and patterns in your life. There's an article about how to build these, super fun, and they show all 4 patterns depending on what question. So pinhole camera, there's a little pin, this is graph paper, and you can look at how does the distance from the graph paper to the hole it slides in this tube? How does the distance affect the size of the image? All 4 patterns show up there, and we're just 3 minutes away. We always want to end on time, so I'll just say, I think we answered every question in the idea capture tool. So we wrote our responses in blue, and always glad to have community responses in there. But here's an exit ticket. If you would, it's really short. If you don't have a lot of time, just what went well, what didn't go well. You can answer just those 2 questions. The other ones, we do read every single one, so always appreciate it. What would make this webinar better? I'm on a roll, so quick remind you, tomorrow is the basics of Desmos. If you want to get in there and just learn how to make Desmos yourself, not mission critical. All the Desmos are set up that students can just click into them and use them, but sometimes students break the error bar. So we'll teach that. There's the workshop on September 7th, where we'll actually take a much deeper dive into each experiment. How do you set it up? Look at the card sorts for each one, all of that good stuff. And we're pretty close, and we have a way of ending, but I'll do a check-in with Matt on just before we do our countdown. Any last comments or anything to say?
No, if you don't mind stopping your screen share, and that exit ticket is in the chat there. We've enjoyed being with you today and would love that feedback here. So yeah, Bradford, do you want to take it away?
Sure. I do like it. Some people like this, some people don't. But if you're willing to unmute, we just do a 3, 2, 1, bye. We'll stay on for a couple minutes. Sometimes there's just questions that people had that they didn't want to ask during the webinar. But if you are willing to unmute and even turn video on, just if you feel comfortable with it, we'll do the 3, 2, 1, bye, and then sign off. But we'll stay on for a couple minutes if there's just questions. All right, so if you're ready, we gave everyone time. Yeah, nice to see people's faces. So 3, 2, 1.
Bye.
Bye, everybody. Bye.